The method of Lagrange multipliers. The method of Lagrange multipliers. Many practical optimization problems involve maximizing or minimizing an objective function subject to one or more constraints. The constraints may be the equation that describes the boundary of a region, or it may not be. Such constraints tend to complicate optimization problems. In this section, you will study an ingenious techniques for solving such problems. It is called the method of Lagrange multipliers. This technique is based on the following theorem. Theorem 21. This is Lagrange's theorem. Let f and g have continuous first partial derivatives. In same region D in the plane. If f function has an extremum at a point AB, on the curve gxy is equal to k, lying in D, and grad g at the point AB is not equal to 0. Then is a real number lambda such that grad f at point AB is equal to lambda grad g at point AB. The number lambda is called a Lagrange multiplier. Not that. This kind of arguments also applies to the problem of finding the extreme values of f, x, y, z subject to constraint g function x, y, z is equal to k. The only thing you need to do is to replace AB by ABC. The method of Lagrange multipliers uses Lagrange theorem to find the extreme values of a function f subject to a constraint. We state it for the case of functions of three variables. Let f and g satisfy the hypothesis of Lagrange theorem. And let f have a minimum or maximum subject to the constraints. G is equal to K. To find the minimum or maximum of f, use the following steps. 1. Simultaneously solve the equations. Grad f x, y, z is equal to lambda grad g x, y, z, and g is equal to k. Step 2. Evaluate f at each solution point obtained in the first step. The largest value yields the maximum of f subject to the constraints g xy is equal to k, and the smallest value yields the minimum of f subject to the constraint g xy is equal to k. Some applications involve maximizing or minimizing an objective function f subject to two or more constraints. For example, we want to optimize f x y z. We want to optimize f subject to the constraints g x y z is equal to k1 and h x y z is equal to k2. It can be shown that if f has an extremum at ABC subject to these constraints, then there are Lagrange multipliers lambda and nu, such that grad f at point ABC is equal to lambda grad g ABC plus nu grad h ABC. We will see an example of this kind of optimization problem. Example. There is a rectangular and there is an ellipse. Ellipse and rectangular. This point x, y. X-axis, y-axis, origin. Find the maximum possible area of a rectangular sheet that can be inserted into the ellipse. Given by x squared divided 9 plus y squared divided 16 is equal to 1. That is, what values of x and y give the largest area. Find the dimensions that give the largest area. Find the maximum possible area of a rectangular sheet. Ellipse equation, this. Let x and y be the vertex of the rectangle in the first quadrant. This is this area x, y. This area is first quadrant. First quadrant, x is bigger than 0. X, y. Y is bigger than 0. Its area is given by this area is x, y. This area is x product y. So total rectangular is f x y is equal to 4xy. This is objective function. I want to maximize this area. Your choice of xy is restricted to first quadrant points that lie on the ellipse. Ellipse equation is x squared divided 9 plus y squared divided 16 is equal to 1. Constraint equation gxy is equal to this ellipse equation. Since grad f x y what is the meaning of grad? Del f del x I del f del y j. So del y I plus del x j. Grad g is similarly del g del x I del g del y j. So 2x divided 9I plus y divided 8j. According to the theorem, grad f x y is equal to nabla grad g x y. So 4y I plus 4x j is equal to 2 lambda x divided 9 I plus lambda y divided 8j. So this equation like components and rewriting the constraint equations lead to the following systems of three equations in the three variables x, y, and lambda. For y is equal to 2 lambda x divided 9. For x is equal to lambda y divided 8. And constraints x squared divided 9 plus y squared divided 16 is equal to 1. First equation, second equation, and third equation. Firstly, from the first equation, you obtain lambda is equal to 18y divided x. And substitution into the second equation produce substitute lambda for x is equal to 1 divided 8y product 18y divided x, and x squared is equal to 9y squared divided 16. Substituting this value for x squared into the third equation. And the third equation gives y squared is 8. So y is equal to plus and minus 2 roots 2. Because it is required that y is bigger than 0. Choose the positive value and find that x is equal to 3 roots 2 divided 2. So f max is maximum value of f function is 4 xy. So for 3 divided 2 product 2 roots 2 is equal to 24. Now another example. Example. Find the maximum and minimum values of the function f x y z is equal to x plus 2y plus 3z, subject to the constraints x minus y plus z is equal to 1 and x square plus y square equal to 1. There are two constraints. Write the constraint equation in the form g x y z is equal to x minus y plus z is equal to 1 and h function x y is equal to x squared plus y squared is equal to 1. Then the equation grad f is equal to nabla grad g plus nu grad h. Grad f is equal to del f del x is equal to 1. So I plus del f del y is equal to 2 to j, and del f del z is equal to 3 k is equal to nabla grad g del g del x is 1 I, and del g del y is equal to minus 1, and j, and del g del z is equal to 1, so plus k plus nu grad h del h del x to x I, del h del y is equal to 2y j, and so I lambda plus 2 nu x I plus j 2 minus lambda plus 2y nu j, and lastly lambda k. We solve the equations. One equation is 1 is equal to lambda plus 2 nu x. Second equation is 2 is minus lambda plus 2 nu y, and 3 is equal to lambda 1 2 3, and first constraint is x minus y plus z is 1, equation 4, and second constraint is x square plus y square is equal to 1, equation 5. And this equations gives nabla is equal to 3, and we write this nabla is 3, so minus 2 is equal to 2 nu x, and x is minus 1 divided nu, and nabla is 3, so y is 5 divided 2 nu, and this is x, this is y. X is minus 1 divided nu, y is 5 divided 2 nu, and then 1 divided nu square plus 55 divided 4 nu square is equal to 1. So nu square is equal to 29 divided 4 and nu is equal to plus minus roots 29 divided 2. Then x is minus plus 2 divided roots 29 and y is plus minus 5 divided roots 29 and from 4 z is equal to 1 minus x plus y is 1 minus plus 2 divided root 29 and plus minus 5 divided root 29 and z is 1 plus minus 7 divided root 29. So C1 is 2 divided root 29 minus 5 divided 29 and 1 minus 7 root 29 and C2 is minus 2 divided root 29 and 5 divided root 29 and 1 plus 7 root 29. F C1 calculate easily. 2 and divided root 29 minus 10 divided 29 roots and 3 product 1 minus 7 divided root 29 is equal to 3 minus 29 and FC2 calculate easily again and is 3 plus 29 roots. This is minimum value. This is maximum value. This is solution.